NMR, let's see where we left off at. Carbon NMR, carbon NMR. Okay, we looked at this. Coupling at the top, decoupled, we were able to see this one peak. Basically, this is how it's typically done. I will give you coupling on all of my problems. The ones in the workbook have coupling for carbon NMR. Okay? I give that to you written above the singlets. We'll look at those a little bit later. So we saw that there. Let's look at some example spectra, carbon NMR spectra. Obviously it's 0 to 200, so we know it's carbon NMR. Everything's singlets, so we also know it's carbon NMR, etc., etc. Here's a compound here. Look at structure. How many different carbons? How many signals do you expect? 8. Any symmetry in the ring? No. No. 6 carbons there. How many more? 2. 6 and 2 is 8. Okay. Here are your 8 signals. 1, 2, 3, 4, 5, 6, 7, 8. Let's assign them. Which one is this?
The ketone. Yeah.
Yes, that's your carbonyl. Way downfield, about 200. Which one is this way upfield? Warren? Just like proton, way upfield is your sp3ch or sp3c. What is this? That's a CH3 here, yeah? What's aromatic region in carbon? 140, 120, 160, somewhere in there. Okay? Here are your 6 aromatics. Okay, which is which? Okay. With aromatics, it can be difficult. We can use shielding, de-shielding, etc. But sometimes there's other things going on. And actually, in the sulfanilamide lab this week, and I sent you this by email, you can use tables and you can actually calculate precise expected chemical shifts based on substituents. And we will look at that handout at some point. I'm not going to do that here though. How much do we need to be able to do? Well, one thing I want us to be able to do is to deal with short peaks. Each one of these signals is for 1 carbon. 6 signals, 6 carbons. But look, that peak is short, this was tall. If we integrated this, that would probably integrate for 1, and that'd integrate for maybe 10. Does that mean that's 1 carbon and that's 10 carbon? No, integration doesn't work for carbon. I see 2 short peaks right here, noticeably shorter than the other 4. Which 2 do you think these are? If we number this 1, 2, 3, 4, 5, 6, which 2 are these here? 1 and 3. 1 and 3. Now I'm not saying which is which. Now I might give a good guess. I want you to know that those are your 1 and 3 because short peaks don't have an H. 1 and 3 carbons don't have an H. Just a shorter question.
Couldn't we kind of guess the one for the downfield was one because of the nitrogen?
You can tend to guess, but again, sometimes you can be wrong with aromatics because other things are going on. Okay, so what are these 4 here?
2, 4, 5, 6.
2, 4, what, 5 and 6? So that right there is all I really expect. Okay? And on a test or a quiz, we would say assign peaks. That's really all I would expect right there.
So you don't have to differentiate between those? You just
Don't have to differentiate between those 4. Okay? I do want you to be able to use, identify, and understand what short peaks can mean. See how the short peaks work? Okay? There you go. Let's look at the one below. How many signals do we expect down here? Don't look at, just look at structure.
5.
Here we have symmetry. The ring is only going to get 4. You got carbonyls 1, that's 2, that's 3, that's 4, that's 5. Oh, that's it. Well, what is this over here? That's 3 prime, and this is 4 prime. It's the same thing. Total of 5. Here are your 5. 4 in the aromatic region. What is this here?
Carbon.
Carbonyl. Some people say tomato, some people say tomato. I don't think many people say tomato though. What do we got here? 4. Huh. 2 are tall and 2 are short. Which ones are short? 2 and 5 are going to be short. I don't know which is which, but I know up to 2. 1 is 2 and 1 is 5. And what are these here? 3 and 4. Now, in terms of integration, there are 2 3 carbons where there's only 1 number 2 carbon. But this signal is twice as tall as this. Height doesn't always count. Area under the curve. But still, those 2 are notably short, as expected. Precise values are given here. That's the way I typically do it. But you can also just guesstimate from the baseline. Obviously, this is like 189 or something. Well, it's actually 190. It's right on the. Okay. How about this? There's obviously no ring in this structure. How many signals do we expect? 4. 1, 2, 3, 4. That's 4 prime, right? What is this here? 1. Carbonyl. Oh, we got 3 down here. We should, for a total of 4. We got 1 that's more downfield. Which one is that? 2. Next to carbonyl. 3 and 4. Now, integration does work a little bit because there's 4. There's 2 of the number 4 carbons. I'm thinking that that's probably 4 here, and this one is 3 here. Just because they both have H's on them. But because there's 2 number 4 carbons, I would expect a taller peak. Unless it's just something weird going on, but I'm pretty comfortable in saying the shorter one is 3. Cause of integration.
I know it's something that has no H's, it affects how fast it relaxes, but if it only has 1 as opposed to 2, 3, does it?
Doesn't matter. If it just has 1, it's going to work. It's going to, only if it's missing any will it relax slow. Okay, how many signals? 1, 2, 3, 4, 5. No symmetry. What is this? Here's your carbonyl. Down here, this is probably 2. Basically, you could be wrong, but I'm going to say this is probably 3, 4, and 5. As you move away from the carbonyl, you're going to be more upfield. But like 3 and 4, you could be wrong. It's very hard to tell. I mean, I don't know how you would tell.
So since 5 has 3 H's and 4 and 3 have 2, we expect, or we expect 5 to be higher, or is just 1 hydrogen here and there not really noticeable difference in terms of?
Well, that's what you just asked here. The only time you're going to get a shorter peak is when it has no hydrogen.
No hydrogen.
It has 1 hydrogen. It may be just as tall as if it has 3 hydrogens. That finishes up carbon NMR. We need to do some comprehensive problems, but before we do that, let's go back to proton where we skipped a couple of pages. Peak splitting, we talked about that. Ultimately, we boiled it down to the n+1 rule. where n is number of non-equivalent. Let's look at coupling constants. Okay, we're back to proton NMR. Coupling constant's a bit miscellaneous, but it's still very important, very applicable. This deals with the distance between lines in like a doublet. Not all doublets are the same. You can have a doublet that is like this. That could be maybe a doublet 2H. Or you can have a doublet that is like this. Okay? These are said to have different coupling constants. It basically refers to the width between your lines. Larger coupling constant, smaller coupling constant. This value, which is a coupling constant, is also known as a J value. J values are given not in ppm, but in hertz. Okay, basically up there is what I just drew on the board. Let's look at some different coupling constants for different type of structural patterns. Typical coupling constant for adjacent H's, like we've been dealing with, is about 7 hertz. These will couple, right? Because they're within 3 sigma bonds. The coupling will be 7. What will these couple?
No.
You're too far away, and so you don't get any coupling. And so you don't get any splitting. And so it would not be any distance between lines. There'd be no separation. It'd be one line. And that's why that's 0. Now, what about H's on the same carbon? That would be called geminal coupling. Now, like if that's a chlorine and that's a bromine, these are different. They'll give 2 different signals. And if they're different, they will split each other, and they'll each be doublets. And the doublets will have a coupling constant of about 2 hertz, which is real narrow. Something like this. Now, we said greater than 3 sigma bonds, no coupling. You can get coupling with greater than 3 sigma bonds. That's 4 sigma bonds or more, if there's a pi bond in between. That's called long-range coupling. And sometimes when we look at aromatics, we'll see long-range coupling. But basically, let's just say we're not going to see it, okay? Sometimes it can happen. It'll be real narrow. Okay, the most important here, the most useful is right here. Your alkenes, but not geminal, but the bissel. Different carbons. If the H's are trans, it's going to be about 15 hertz coupling. If it's cis, 10. Relative though, which one gives greater coupling, cis or trans? Trans gives the greater coupling. This coupling can sometimes help you identify between cis and trans. For example, look down here. What if you knew you had one of these compounds, and these are just cis-trans isomers, or EZ isomers. Here the H's are trans, they're cis. But when they're trans, you expect greater coupling. First off, what do you expect in terms of this signal here? Singlet, doublet, what?
Doublet.
There's one H neighbor, so this would be doublet. 1H, what would this be? Split by that guy. See, they're splitting each other. They're each doublet 1H. But is it going to be a doublet that's wide, or is it going to be real narrow?
Wide.
Well, it's all relative. It's going to be about 15 hertz. And so there are your 2 doublets. This guy's going to be the same thing. Doublet 1H, doublet 1H. But the doublets will be what for this guy? They'll be more narrow. You see how they're more narrow here. Now it's pretty darn consistent. Trans is pretty close to 15. So if you ran your compound and it came out to be 9 hertz between your doublets, that suggests you have which one? Because 9 is, you know, it tends to be pretty precise, either 15 or 10. 9 is much closer to 10. So that's how you can use it. If you go on to advanced organic and you do advanced NMR, you will definitely deal with coupling constants. Now, there's an exercise down here. I want you to determine the J value in hertz for the most upfill doublet in the NMR of this compound, proton NMR. Proton NMR is given on the next page. Let's see, there it is on the next page, right? Is that it? Yeah. It says the most upfill doublet. Well, which one is the most upfill doublet?
1 on 7.
Now, this is a real NMR, okay? None of these are doublets. Okay, the real NMRs, you get sort of peak picking. It tells you the peak, because there's only one peak pick there, that's a singlet. What is this? What is that, a singlet, doublet, triplet? Doublet, because 2 values were given. Now you can actually expand this and actually see that it's 2 lines. There's your 2 values. But that's ppm. What is the width in ppm? Well, you just subtract the numbers, right? It would be that minus that, so it would be 0.012 ppm. 0.012 ppm. That's how wide it is in ppm. But coupling constants are given in hertz. So we need to convert that to hertz. How would you do that? This takes us back to, what does ppm refer to? What does parts per million refer to?
Concentration.
It can be concentration, or it can be, more generally, it could be, if you got 3 people in a stadium that has 3 people wearing hats in a stadium that has 3 million people in it, how many people in your stadium are wearing hats? 1 ppm, 1 part per million. It's really a kind of a percentage, or it's, okay. So what does ppm mean? ppm, we don't plot exact frequency in HNMR because it varies depending on magnet size. Doesn't the delta E between the alpha and the beta, right? This is a delta E. Doesn't this vary depending on magnetic field?
Yes.
And we did a graph like this. The bigger the magnetic field, the wider the gap. Okay. Well, let's say you're doing people are doing running 2 different NMRs, and let's say here we have a 60 megahertz NMR. Now that's in megahertz. You can turn this into Tesla, which is a unit for magnetic field. But let me just get it like this. Versus 300 megahertz. That's a larger magnet. If you're using this, your delta E may be pretty small. What if we use a magnet that is, 5 times larger? Delta E is going to be this. Okay? Now delta E corresponds to energy, which corresponds to the frequency that's needed to match the resonance. So this here you need lower energy light, or what is that? Lower frequency? Yeah. Here you need higher frequency. And if you plot frequency, you're going to get maybe just very arbitrary numbers. This may be 10 hertz or something, but this is going to be maybe 60 hertz. And then this guy would say, hey, my signal comes at 10 hertz. This guy would say, the signal comes at 60. So who's right? Maybe somebody else is using a super humongous magnet and they get a signal at 100 hertz. So what's the value? Well, guess what? I should have just called this 60 and this 300. Well, somebody came along and said, what if we divide this by 60 megahertz? What do we get? That's 1 hertz out of a million. 60 hertz out of 60 million, it can be put as what? Yeah, 60 out of 60 million. Well, what if we divide this by 300? What do you get? 300 out of 300 million, what is that? Now everybody's happy because now everybody's got the same position in NMR. Everybody's got ppm. The reason we do ppm is because you can use different magnets. But basically we're normalizing by dividing by the operating frequency and it turns it into ppm. In the end, what is 1 ppm? How many hertz is that? It depends on the magnet you're using. If you're using a 300 megahertz, 1 ppm is how many hertz? 300. We need to know what type of magnet was used. It says it somewhere. 300. So each ppm is how many hertz? 300 hertz. So if each ppm is 300 hertz, what is 0.012 ppm? Well, if 1 ppm would be 300, what do you need to do? I haven't had math. Multiply 300 by this? What do you get? What is it? 3.6 hertz? There you go. Now you look at your textbook and they'll give you some nice formulas that you can plug and chug. So I just sort of explained it. Okay? Why is hertz given in, why is coupling constant given in hertz? Because coupling constants do not change based on magnets. But peak position would. Okay. The other page here was complex splitting. We've actually already done that. I didn't take you to this page. Complex splitting is just going to lead to multiplets. You can look at that on your own. Just remember, if the neighbors are not the same, you have to apply the n+1 rule for each type of neighbor. And ultimately, when you start doing that, well, by the way, when you do that, that's called complex splitting. And just about every time you do that, you're going to end up with what type of signal? Multiply, okay? I don't want to take the time to go through that, but we'll look at it.
Dr. Stevens,
Yes?
that previous example where we worked out the math on 3.6 hertz, 2.1 hertz, that doesn't seem to line up with anything.
I thought that's where you were going. Let's see.
In that box of stuff.
Let's see. I can tell you more about that and what that tells me. Yeah. What's not in that table here is your typical aromatic. Benzene is typically 7 to 8 hertz. Benzene coupling 7 to 8 hertz. So because we calculated this signal to be 3 point something. Does that seem like a benzene hydrogen? No. What that tells me is those H's are not in this benzene ring that are giving that signal. Now, what I know is, I know other rings. Typical ring like this called furan, it typically gives coupling in, guess what? About 3 to 4 rings. So by knowing the coupling, I know that that signal is coming from that furan ring. But you can look at tables and you can see all types of standard couplings for different types of systems, and then that can help you identify peaks. Okay, but benzene is usually 7 to 8. So that does not seem to be a benzene hydrogen there. Or the one it's coupling to. It's really, when you do coupling, it's, you got two guys, two partners. Okay. Anything else in this handout? Let's work some comprehensive problems. Any questions about the front page? I had to make a couple of changes to that. I talked to a number of you about that. Question?
On the one where you have like the spectrum overview, it just has the information about the feature names, the NMR.
In the packet? In the packet?
Yeah, it's in the packet. It's,
Where at? In the middle, back?
it was towards the front, it's like 3 pages in.
Uh-huh. Which one?
The spectrum overview is the
Spectrum overview? Spectrum overview?
That only has 3 signals, but shouldn't there be 5?
Okay, good question. Theoretically, yeah, there should be 5. 1, 2, 3, 4, 5. Yes. Which is which? TMS? Let's look back at this now that we know what we're doing. It's a good thing to look at. Oh, we forgot the D20 Shake. That was number 5, which was on the coupling page. Okay. Now ready to do the D20 Shake? Okay. But here, Singlet 2H, Singlet 2H, multiplet. This is aromatic region. First off, why is this one signal? First off, why am I calling it a multiplet? It looks like a singlet. If I expanded this, it would probably be multiple lines real close. Theoretically, you expect 3 signals. In practice, sometimes you only get 1 or less because those 3, instead of being separated out, they may be so similar that they're all just on top of each other. And they're said to be coincidentally similar. I think that's what's going on here. The 3 theoretical signals are just right on top of each other. Is that an answer?
Yeah, but why are they okay, so I understand that, but then the 2 H's, they have neighbors, like the CH2 has neighbors.
Yeah, and the D20 Shake would also tell us something here. I'll go ahead and say it. We need to go back to that page there. Usually you don't see splitting when there's an oxygen or nitrogen between your H's. So another way to say that is, usually an OH or an NH does not lead to splitting. Okay? Usually NHs don't split. Yes, these are within 3 single bonds, but there's a nitrogen in there. Usually you don't see splitting. It can be solvent dependent. So it's like it's isolated. And this one is this here. This one is this here. Just a couple of good questions. But I also see we need to point out a couple other things about the nitrogen oxygen. The first thing is, where do you expect the NH or OH to appear in the HNMR? Let's look at our table. I wrote this in here. In this table, they said 1 to 5. You might think that's a little odd because isn't the nitrogen sort of withdrawing?
Yeah.
Should we move it downfield? Yeah. Well, first off, I hate 1 to 5. I would say anywhere on the spectrum. 'Cause I can show you NH and OH signals that occur at 10, 11, and I remember in graduate school, I had one that was so far downfield, it wasn't even on the spectrum. And I had to expand my sweep width, and it ended up being like 14.8. Okay? So I don't know where they get 1 to 5. Of course, in the example we just showed, it was 1 to 5. Trust me, it could be anywhere. Highly variable, I should have said more. It also depends on sample concentration, etc. One other thing about these signals, so it doesn't match the one we just looked at. OHs and NHs tend to be broad. That is, instead of a sharp signal like this, it may be something like this. Now, let's look at the fifth item here, the D20 Shake. Now, I think this is the last of the numbered topics. The D20 Shake is a sort of a tricky way to identify these OHs or NHs. Identify them. How? You take your sample, usually you run it without the D20, standard run. Then you go back and you add some D20 to your tube. Remember the tube looks like a straw with a cap on it. You add the D20. Yes, you do shake it up so it can mix. Okay? All right? What happens? Your OHs and NH will exchange with the D20. Okay? Now D20 is not an acid, but you still get equilibrium going on. And the D20, these electrons will take the D. Okay? It's very weak equilibrium. This is not acidic, but it does happen. You get to this point, which is a protonated alcohol, but then the hydrogen can be removed. But instead of removing that hydrogen, we can remove, instead of removing this hydrogen, which is a hydrogen with an extra neutron, right? We remove that one. And so the OD minus, take this H, and what do you get? You get OD left instead of OH, plus H2O. But you've exchanged out your H with a deuterium. And now, since deuterium does not give a signal in the proton region, your signal will disappear upon rerunning the sample. It'll be gone. Now, sometimes it's not always gone, sometimes it's just greatly diminished. Because this does establish an equilibrium. You have to add a huge amount of this to get it to go all here. If you add a little bit, you'll have both. Exchangeable protons will be exchanged with D20. Usually these are OHs and NHs. Not CHs. CHs are not acidic. There's some cases where maybe your CH is very acidic and it will exchange, but typically for us it's OHs, NHs. Let's look at an example of this. We've got to flip over. Yeah. Over here, it says D20 Shake at the top, but it got cut off. Compound from the research lab. Lots of aromatics, because we see we got 3 aromatic rings. A little bit about real spectra. Real spectrum is always going to include water. And that's that huge peak here. There's water's everywhere. Okay? You got a sample. Here's my sample. Okay, you're the light source. Okay, throw some light through it. Here's the detector. Okay, and this absorb delta E and stuff. Okay, also relax. Okay, and we got a detector. Okay, is there any water between there and here? Yeah, there's water in the atmosphere. Probably also some water in your solvent, but it's very hard to get. Okay, so there's always water around. You're going to get that signal. It's going to be typically a lot because water has such a low molecular weight. That's water. This is DMSO D6. It's your NMR solvent. Why is it giving a signal if it's all deuterium? Note the deuterium, should that give a signal in the HNMR?
No.
Why is it giving a signal?
Age exchange.
Because usually this is 99.9% D. What's the other 0.1%?
Age.
Yes. That's what gives the signal. Now remember, you use a huge amount of, if we had used, if this was 100% H, this signal would be like as tall as the Mount Everest. That's the residual proton. Now, you maybe can buy 100% D, but you're going to pay a lot of money for it, and it's going to be cost prohibitive. So usually we use like 99.9. Not as expensive. And we just have a little solvent in it. That's the leftover H's there. Okay. What else do we have here? The rest is compound or impurities. What is this here? Is that a singlet, doublet, triplet? Doublet, huh? Do we expect a doublet? Those are two methyls up there. This is actually two singlets. Because I know structure. Why do we expect two singlets? Because you got two isolated methyls. Okay? These are singlets, both two H's. What are these? Well, you see? CH2 or the NH2. Integration is identical. They're both integrating for two H's. Integration, then the numbers don't themselves mean nothing. It's relative. You see, this is 30. How many H's is this? 6H total. So that means each H is how much? 5. That means that's 2, that's 2, that's 2. How many is that? Probably 3, 2, what is that? 2. Is that a 9? Okay, 2. Which one is the NH2?
One of the same ones.
Which one is which?
The one on
The
the one on the left?
How much money are you willing to bet on that?
A lot.
How could we figure out which is which, Lolly?
Add D.
What do you want to add to and rerun? Want to add D2O? Would one of these signals exchange with D2O?
Oh, yeah.
Which one? Okay, well let's add D2O and shake it up and rerun the spectrum. And if we do, we get the spectrum on the next page. Let's see what happened. What happened? Did one of the peaks disappear or greatly diminish? Which one? This one. Much diminished. It exchanged with D2O. What does that tell you about this signal? Which one is this? That's your H2. Now we have proof. If I'd added more D2O, it might have disappeared, but I got my answer. I didn't need to add much. D2O is expensive. Nothing happened to the other signal. It didn't exchange with the D2O. or any of them. That one reduced. Okay, that's D2O. Any other questions? Did we finish the packet? Let's see if we can work a problem here. How about the one in the pre-course handout, pre-course worksheet? You got the pre-course worksheet? Okay, this is the type of problem you'll see on the exam on Monday. Based on the spectral data provided and information in the paragraph, determine the structure of the unknown compound. Molecular formula in this case is given, which gives a positive Jones oxidation test. Chemical test information usually will be given. What does a positive Jones oxidation test mean?
Primary
If it's an alcohol. Because there are other functional groups that would give a positive Jones.
Could be an alcohol.
What is it? What is this not? It's not a tertiary alcohol with nothing else. It's also not a lot of other things. First off, is this an alcohol?
Yeah.
I could have a broad OH. Now what does it say? What is the directions here? Correct interpretation of each spectrum will lead to considerable partial credit. Oh, these usually say different things. In the end, you'll see the ones in the workbook, you need to interpret every spectrum. It's not just to show the compound. Okay? You also need to interpret. If you just show a compound and do nothing else, you're going to get minimal credit, even if the compound is right. At the same time, if you show a wrong compound, but did lots of good interpretation, then you're going to get lots of partial credit. So OH, what is this here? How many DUS in this compound?
4.
Okay. 4. It sounds like maybe a benzene ring, because it has 4. Does it have a benzene ring?
Yes.
How do you know?
It's like aromatics and 7-8.
Oh, H and MR.
It's like disubstituted benzene.
Yeah, H and MR, aromatic region. So if it's got an aromatic ring, well, let's draw these fragments. Remember, let's think horses, not hooves. All right? So benzene ring, but it's got to have something on it. How many substituents on this ring? 2, because there's only 4 H's there. Looks like a pair of doublets. What does this might indicate? The 2 substituents are likely? Looks like it's para-substituted. Okay? We talked about that. Classical pair of doublets. Well, there's your 4 DUS right there. Can this compound have a carbonyl? No, that would be 5, and the formula doesn't support that. And indeed, if you look in the IR, there is no carbonyl. Not much in the IR remaining. Let's look at proton. What other fragments can we get up here?
The singlet 2H.
Singlet 2H. What do you want to say that is?
Bound to ether.
A CH2 that is, what kind of neighbors does it have?
Benzene and ether.
The fact that it's a singlet tells us about neighbors.
Yeah, benzene and ether.
It's isolated, right? Because there's no splitting. It's a singlet. Now it's also way downfield. What's going to make it downfield? Maybe it's nitrogen.
There is no
Oh, formula was given.
Yeah.
Okay, so we don't have to worry about it. So let's bind to an oxygen, that would move it downfield. How many oxygens do we have?
Two.
Okay, 2. Now what I like to do is sort of draw it near here, I'm over there. Maybe something like this. Singlet 1H. D2O exchangeable, singlet 1H, what could that be?
Battle?
That's the
Oh wait, does it come out and have an OH? IR says it does. If there's an OH, there's got to be a signal in the H and R for the OH. D2O exchangeable, that's free information, right? We know what to do with that. So what is this? It looks like the OH. Of course, it's not way downfield or broad like I told you they often are. Believe me, you'll see some that are broad. The more acidic they are, the more broad and downfield. What is this, quartet and triplet? It looks like they're maybe
Together.
coupling to each other or something. Quartet 2H, that means it's what, a CH2? What's next door? CH3. Would that be a quartet 2H?
Yes.
Yes, what would this be? Triplet 3H, do we have that?
Yeah.
Yeah, we sure do. That's a nice ethyl. Now, can this be another CH?
No.
No, that would make that complex splitting. That would no longer be a quartet. So this is sort of cut off. We got fragments on the board. How many carbons do we have on the board? 6, 7, 8, 9. How many in the compound?
9.
How many H's do we have on the board? 4, 9, 10, 12. How many in the compound?
12.
And we got two O's on the board. Everything's on the board. Now you just got to put it together. Okay, I'll start with this. Variety of ways we can put it together. I got an OH. I can put what here? The ethyl? Well, then there's no room for that.
No. With the CH2.
About the OCH2, and then put the ethyl.
No.
It's split.
Can't do that because then that will be next to the CH2. How about this? Does that still fit?
Yes.
Is this still going to be what we expect? Yeah. Is this going to be a singlet 2H?
Yes.
Is this it?
Yes. Maybe.
Could we have had another answer?
No.
This is not it. This is not it. We can make, because this is match the Jones oxidase, the chemical test.
Well, yeah.
Chemical test tells us we have what type of alcohol? Primary or secondary. Here's the thing, phenols typically do not give a positive Jones. Could. Let me show you. Hold on. Could we put this together another way? Maybe that is it.
Do you just have the CH2 attached to that?
Do we have mass spec? By the way, we haven't even used carbon NMR. We do need to assign peaks. If you look in the workbook, the answer keys show you how to assign all the peaks. Okay? So on the test, you need to do it just like in the workbook. Think about this. Is there another way to put this together? I think there may be.
With the OH and the CH2 and then
Let's look at it on Friday. Okay, please be doing problems in the workbook.
details, like, my college and stuff like that. I don't go get all those. The test, like, don't practice any of these. Test
Zoning out? Are you zoning out?
He did. Now that's,
I got a report.